Last class, well, probably every class, I say things that I think are perfect. I realized people didn't know what I was talking about. So one thing I mentioned last class was your lab is like Macgyver. And I found out that a lot of you don't know what I'm talking about. So Macgyver is this guy on a TV show, and he gets himself in trouble, and he doesn't have anything with him, and somehow, over and over again, he just takes whatever he has available to him, and he makes it work to his advantage. And to see what it looks like, here's what Macgyver looks like on TV. So whatever it is, he can make a little machine, and he makes it all work out. Okay, so that's how you're supposed to feel when you're doing the lab this week. You just, somehow or other you got yourself stuck in that room, and all you got is Lego and some valve and some hot water and some cold water, and you just got to make the whole thing work. And if you're lucky in your life, you get that sensation in other things you do, that somehow you make do with what you got and you make it work. Now, usually in engineering practice, in fact, we just rewrote that lab for you. The way that lab was written for the people who did it last year, you can look in the old report, is you're supposed to make design drawings, and you're supposed to consider the pros and cons and do an analysis and show your TA and blah, 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 and then you're supposed to implement your design. That's the way we try to teach people how to do design. In fact, the way real people really do design is probably a lot closer to the Macgyver thing that you do in the lab. You just try things that don't work, you try something else, it doesn't work, you try something else, you improve on what does work, and so on. And that iterative process is probably, I think, much closer to real design than this concept of careful analysis. On the other hand, every now and then, you want to look at what you've got and do an analysis and understand it. And an example of one of those analyses is this hydrostatic thing, which I'm having trouble communicating to you yesterday, and I'm going to try and do it again today, and I'm going to try and move on and talk to you about how to do it with the computer. Before that, do you have a clicker with you? Register your clicker. Anybody have any votes they would like to take in the room, like they'd like to find out about their classmates? Anybody curious about other people's opinions about anything? Nobody's curious? I'm sure you are. What? A if you vote yes, and B if you vote no. Whatever question you want, that's your business. I don't want to intrude on your privacy. Now, how is it that 97 people are voting when there are only 56 people in this class? Right?
Everyone is
This is a tough one here. Let's try again. Okay, ready? Everybody vote again. Vote yes if you're in favor, and vote no if you're opposed. And just keep it to yourself what it is you're voting about. 56, 57, 58, 58, 58, 58. Going once, going twice. 59, 59, 59. Sold at 58. Okay. Okay, so you had this problem. It was due last Thursday. My understanding is that next to none of you actually finished the problem, which is okay. But it's not if you all can do it easily, it's not a challenge. What's the point in giving you a problem that you know how to do? So the problem was you have this ball which has half the density of milk and is floating in the milk halfway up. And then you pour oil on top, and as a consequence of pouring the oil on top, the ball goes up. And why it goes up instead of down, I explained with the demo, with the cork and so on. And if you don't understand it, you should think hard about it or come talk about it. Okay, now, we'd like to know how much it floats up. So let's just skip this here for a minute. And we know from Archimedes' principle that the buoyant force is equal to the weight of the displaced fluid. And we know from statics that if this thing is static, the weight of gravity pulling down on the ball is equal to the buoyant force. What's the weight of gravity pulling down on the ball is the density of the ball times the volume of the ball. What's the buoyant force? It's the displaced fluid. What is that displaced fluid? It's the density of the oil times the volume of the ball that's under the oil. And it's the density of milk times the volume of the ball that's under the milk. So this is our basic statics buoyancy equation. It says that the weight of this ball, that's the gravity force going down, is the weight of the fluid that would have been here plus the weight of the fluid that would have been up here. Any questions so far? Now we would like to do some algebra with that. How do we go about that? Well, you were told some relationship between these densities. There's too many variables in here, and you want to reduce this to something you can solve. Feels like a 1 degree of freedom problem, so we should get it down to one variable. We were told that the density of the oil was half the density of the ball. That is, that the ball sinks in oil. And we were told that the density of milk was twice the density of the ball. The ball floats in milk, like in the first picture. So by doing that, we get rid of these two densities, and we've got things only in terms of the density of the ball, which crosses off of this whole equation because there's the density of the ball all the way through the equation. Now we've got the volume of the ball, and some part of it is submerged in milk, and some part is in oil. Say the fraction of the ball of the volume that's in milk is F. Therefore, the volume in milk is F times this volume of the ball. And the ball's only got so much of itself, like 1 of itself. So the fraction of it that's in the oil is 1 minus F times the volume of the ball. Now what happens here is that the volume of the ball crosses off of both sides of the equation. And then you get this equation, one equation for the fraction of the ball that is submerged in milk. And you can do algebra on this. It turns into this. And it tells that 1/3 is in the milk. And I don't know, half the class got that right, roughly? A third? Solve for the unknown. 2/3, one fraction of the class did it, but 1 minus that fraction did it, times the probability that they know it. It came out 1/3 got it right. Okay, so anyway, some of you got that, some of you didn't. Given this answer, then the question is, how high does the ball float? Now, this was the algebraically, mathematically hard part of the problem, and that's what I was starting to work on last time. So in order to figure out how high the ball floats, we need to know a relationship between the height of floating and the volume of the ball that's in the oil and the volume that's in the milk. Now, we'd like to say, given the volume, what's the height? But almost never in engineering practice can you just write a formula for the thing you want. What you do is you try to say things that are true and use algebra to find the thing that you want. So that's the method of solving problems. Just say things that are true and use algebra to find what you want. So in this case, what we think is if we knew the height, we could find the volume. Well, if we knew the height, we can find the volume. We could make a plot of height versus volume, and then we could solve for what we're interested in terms of that plot. So we'd like to know what the volume submerged is as a function of height, and then we're going to try and solve for that height that makes it so 2/3 of the volume is up here. Then we get to this calculus problem, which is how do we calculate this volume given this height? And the way that we calculate it is we say the volume in oil, all this stuff up here, is the sum of three volumes. It's the sum of this VHS, this half cylinder, half sphere, which is 2/3 pi r cubed. It's the volume of this cylinder here, V sub c, which is pi times the radius of the cylinder. And if this is an r and this is an h, the radius of the cylinder, this distance here is the square root of r squared minus h squared. And the volume of this cylinder is pi times that radius squared times the height of the cylinder, plus this volume here, which is this integral, which I set up last time. I do not claim, when I set up that integral, that this is the easiest way to do the problem. This is just a random way to do the problem. Probably it's not the easiest way to do the problem. But it doesn't matter. You just can crank your way through and work out what we're trying to find. Now what we're trying to find is the volume of this thing here, of this cylinder here. Yesterday's class I had this flipped upside down just to make it so you don't have to go upside and back. I've left it upside down here. So how do we figure out this V? Well, we've got to figure out the volume of this funny shape here. It's this region here that we're trying to find the volume of. That's the thing we called V. And the way we set about trying to find the volume of it is we divided it into cylinders like this, and we tried to add up over all these cylinders what the volume is. And in order to do that addition, I parameterize these cylinders by this angle, which I call theta. And that theta ranges from 0 up to what I could call here theta 1. And one of the confusing things I did last class is I changed theta 1 to theta 2 and theta 0 to theta 1. And I know what I'm talking about, but you don't. So I'll try to be more careful about what these angles are. So now we want to figure out this volume V. And we say what the volume V is the sum of all the bits of volume dV. Where by dV, we mean the volume of one of those little cylinders. How do we figure out the sum of those bits of volume dV? Well, we've got to look at the height. It's blinking, it's erratic. It's low battery, right? Here, you work on this. Is the camera on? Okay. So we need to figure out this H in terms of theta. So here we have R theta, so H is R sine theta. That's the quantity H when we set up this integral. That is capital R. Now if we want, we can do more algebra and figure out and get a formula for the volume in terms of H. In order to get a formula, now you think it's working? We need to get a formula for this thing.
How do you get R cubed when it comes out?
R. R times R times.
Okay. I thought that was.
And a 2 pi. Okay, now we want to do this integral. We can do the substitution. This is u squared du, which this turns into then 2 pi r cubed times the integral from 0 to u. So this is from 0 to sine of theta 1 of u squared du. And this then is 2 pi r cubed times u squared du is u cubed over 3. So this is u cubed over 3 evaluated between 0 and sine theta 1. But r times sine theta 1 is capital H. So this turns into 2 pi times h cubed over 3. So this gives us the volume of that sliver. This is the thing we called V. And then we can go back and we can say, therefore, V in the oil is equal to our volume of the half sphere plus the volume of the cylinder plus this thing I called V. And the volume of the half sphere was 2/3 pi r cubed. The value for the volume in the cylinder was pi times r squared minus h squared times h. R squared minus h squared times h. And then this volume that we just figured out, this V, is 2 pi h cubed over 3. And then if we want, we can try to simplify this expression. For example, we can pull out a pi and write it this way or that. But the main thing is that we get this volume in oil, and what we have is a constant term, and we have a term proportional to h squared, and we have a term proportional to h, and we have a term proportional to h cubed. So we have a C0 plus C1h plus C2h squared plus C3h cubed. And there's different ways of factoring it this way and that, but what we get is a cubic expression for the volume of the sphere as a function of h.
Wait, can you repeat what you did again with the C's?
What are the C's? What I've done is just collected terms that have to do with powers of h. So for example, C0 would be this 2/3 pi r cubed. And where's the term that's linear in h? That would be pi r squared. So this pi r squared would be C1, and so on. Okay, so as far as h is concerned, it's a cubic formula. Now what we wanted to find out was, our goal was to find h so that V oil divided by V of the whole sphere is equal to 2/3. Because that's what we said. The volume that was in oil was 2/3 of the total. What does this mean we have to do? Well, this is a constant that we know. These constants we all know. This means that we have to solve a cubic equation. which in practice you have to do either graphically or numerically. Yes?
What happened to the square root of R squared mass?
The volume of this cylinder is this radius squared times the height.
Yeah.
This radius is the square root of capital R squared minus h squared, and then we have to square that to get the area of this cylinder. So it's the square root squared gets rid of the square root. Yes?
Would you limit go from 0 to theta 1 to 0 and sine theta 1?
I made the substitution that u is equal to sine theta, and when we made that substitution, we had to also substitute the limits of integration. So this is from 0 to u1, but u1 is sine of theta 1. Go ahead, ask out loud.
He was asking how is dr equal to r sine theta d theta?
Where does this come from? This is the relationship between this little sliver of angle here and this little sliver of length here. And you just draw triangles. Look at your notes from last time. I tried to draw it carefully. And you see that the bigger d theta is, the bigger dr is. That scales right. The bigger r is, the bigger dr is. That scales right. And when theta is very small, we get a very small dr because the projection of this onto this line is very small. So that's got to be like a sine theta. So it's got all the right scalings and trends. Any questions about this? Okay, so what happened with this problem is that by doing all this calculus, we ended up with a problem we still couldn't solve with pencil and paper. We're stuck doing it numerically. And this is most often what happens in engineering practice. In fact, most often in engineering practice, after you set up this integral, you don't actually get one that you can solve. So it happens that this was an integral we could do. If you use the method of disks, you get another easier integral to do. Maybe there's some other way you could do it. You get an integral you can do. But in real engineering problems, you would be very lucky if you get an integral you can do. So what I wanted to show you is what do you do if you get an integral you can't do? And what I want to show you is not the fancy, best, most efficient, super deluxe. I want to show you the Macgyver way of doing things, which is really the way you'd like to be able to do things, which is your own scrappy way of getting the problem done. So I don't want to use all fancy things. I just want to take dumb things as we understand it, put it together, and figure out how to get this answer, assuming that we did not know enough calculus to go from this point on. Now, how do we do that? Is that we take this thing and we say this volume of interest is not an integral. It's approximately equal to a sum of little volumes. And those were the volumes of the cylinders. And in particular, each of the cylinders has approximately the value of r sine theta multiplied by 2 pi r cosine theta multiplied by r sine theta delta theta. It's the thickness of the cylinder, the height of the cylinder, and the circumference of the cylinder. This is the formula that I was hoping that you would feel comfortable with from the pictures I drew last time. And when I say this is something that you should know how to do, I really would like you to know how to do it. I really would. That is, you want to know how to go from pictures to assembling sums like this. And of course you want to know how to go from sums like this to turning them into integrals like this. But right now I want to focus on the Macgyver approach, which is we don't really know calculus. We're just going to approximate this volume as a sum of things that we understand. We never heard of calculus. We're in high school, we never heard of calculus, and we're trying to do this problem, which means we're trying to figure out what this volume is as a function of h. We know the formula for the volume of a half a sphere somehow. We know the formula for a volume of cylinder somehow. We're trying to figure out the volume of this weird shape spun around here, and we're going to do it by figuring out the volume of these little Coke can slices and adding them up. And we're not going to add them up using calculus. We're just going to add them up, period. We don't know integrals. We don't know derivatives. We don't know the fundamental theorem of calculus. We just know that this volume is about the sum of the volumes of these thin little cylinders. In each of these cylinders, we know how to figure out what it is because we figure out the height of the cylinder, we figure out the circumference of the cylinder, and we figure out the thickness, all using high school geometry trig algebra. Yes? Comfortable with that? Okay, so now we want to do that, and I want to show you how to do it on the computer. We don't know calculus at all. You know trig, you know geometry, and we're just trying to figure out what that volume is by just adding. Now it turns out adding is integration, and we can use formulas, but often the formulas don't work, so we want to go to the Macgyver approach to this numerical method. So the first part of the Macgyver approach is you're stuck in a room and you have a bad projector and you try to make the most of it. So what you do is you pass the controls to a student and you ask them to up the contrast. So they did that already. Next thing is you try to pull down the shades. Now, let's see. I should climb a ladder and unscrew this bulb. Dare me to do that, right? Okay. I'm going to fail that Macgyver challenge. Okay. Can you read the text on the screen? Any trouble with it? Who has trouble with it? Somebody said yes, they have trouble. You have trouble? There's like 5 extra seats up here in the front. Anybody else have trouble? Just come on up. Go ahead. Don't be shy. Go ahead. Go ahead. Go ahead. Okay. So what I've done is I've written a script file here in MATLAB. And what's a script file? It's a bunch of MATLAB commands. I've named this script file sphere.m. So here I have sphere.m. And what this is just a sequence of commands which is trying to figure out these volumes we're after. Let's just say, to start with, that the radius of the big sphere is 1. And let's say that the height we're interested in is 1, which means I'm going to look at the special case when the height is the total radius of the sphere. So when the whole thing is an oil. And you'll see why I do that. And what I'm going to do is try to figure out the volume of that weird shaped sliver by dividing it into 100 cylinders. And to do that, I have to set n equals to 101, because if you take the number, if you want to take from 0 to 1 100 pieces, and you have the 0 piece and the end piece, you got to put that extra 1 there. Okay, so now what are the angles theta? I'm choosing to make my thing that I add over theta. So I'm going to take little delta thetas, and for each delta theta, I'm going to figure out the volume of the cylinder. What are the values of theta? Well, I'm going to divide it into 101 pieces. So I take the number from 0 up to the biggest value of theta, which was the arc sine of h over r, and I'm going to divide it into 100 pieces. So this is this command linspace in MATLAB. Okay, with me so far? Yes? Raise your hand, yes? No? Okay. Now, I've got to figure out the volumes of all those cylinders that I'm going to add up. Well, they're going to be related to delta theta. In fact, they're going to be proportional to delta theta, the volumes of those cylinders. And now I have to figure out the proportionality constant. But first of all, in this method where I'm going to add up 100 cylinders, how big is delta theta for each cylinder? Well, it's different. It's the difference between the max value and the minimum value divided by the number of values, which is n minus 1. Because there's only n minus 1 intervals there. And the command max, if you have a whole list of numbers, remember theta is a big long list of numbers. The command max pulls out the biggest value of that list, and the command min pulls out the smallest value of that list. So max is a MATLAB command, min is a MATLAB command, and linspace is a MATLAB command. All useful MATLAB commands. Then I've got to look at the heights of each of these cylinders. Well, the height is r times sine theta. And this is now telling me actually 101 heights. Or, yeah, 101 heights. And I've got to figure out the radii of all of these little cylindrical shells, and this is 101 radii. So I've got 101 values of the angle corresponding to these 100 cylinders, and I've got 101 values of the height and 101 values of the radius. And I've got to look at how thick is the cylinder. Well, the thickness of the cylinder is proportional to delta theta, and it's also proportional to sine of theta. So now I have 101 delta r's. And I didn't have to put a dot times here because delta theta was just a scalar. There's only one delta theta. I'm going to just evenly pick the same delta theta all the way through. So I didn't need that dot there. Okay, any questions so far? So now I've got 101 values corresponding to these 100 cylinders. I've got the thickness of the cylinder, which is this delta r.
Excuse me.
Yes?
Could you please repeat why you take n equal to 101?
Because I want to look at 100 cylinders, and I've got, if I wanted to, let's say I take the numbers from 0 to 1 and divide them into 100 pieces, and I go, okay, 0 up to 0.01, up to 0.02, up to 0.03, up to 1, and I look at how many numbers there are there. There are 101 numbers there. But I didn't have to put 101. I could have put 100. I just I thought, I mean, I can put 97 here. It's not going to change anything. Okay, it's not going to change anything very much. Now, MATLAB can do all kinds of tricky things. So I'm going to go over here in the command window, and you've seen this already. Let's say I do clear, which means it doesn't know anything. Now if I say x is equal to 5, it knows that x is equal to 5. But if I put x sub 2 is equal to 6, what does that mean? Because x was just a single number. MATLAB all of a sudden knows that I mean for x to be a list of two numbers. So it does this so-called dynamic memory management. It tries to think what you mean. But that takes a lot of time on MATLAB's behalf. By the way, what happens if I put x sub 4 is equal to 7, to 8? What would happen to x sub 3? Does anyone know? Yeah. Good guess. Okay. So here we're going to try to figure out all these things which are going to be so-called partial volumes. So when we do this adding up of these cylinders, we're going to add up this cylinder plus this cylinder plus this cylinder plus this cylinder. But as we go, we can save up the volumes so far. So I can have a sequence of partial sums, which is the sum of the first cylinder, then the sum of the first two, and the sum of the first three. And I save that as a big list. And that's what I'm calling V. And rather than having MATLAB have to figure out over and over again how many they're going to be, I'll tell it ahead of time, they're going to be 100 of these things. Or 101 of them. Now, in the end, we're interested in the total volume, and that includes the half sphere and the cylinder. So we have total volume is this. The half sphere is just 2 pi r cubed over 3. Remember, we had to add that back in. And let's just say that the total volume, that cumulative sum, right when we start, it's going to be the volume of the half sphere, because even if little capital H is 0, we still have half the sphere is in oil. In oil. Okay, now we want to add things up. So what we'd like to do is we'd like to add up all of the cylinders. So each cylinder has a volume of 2 pi times the radius of that cylinder, which we already figured out was capital R sine theta, times the height of that cylinder. Sorry, that was capital R cosine theta. And the height was capital R sine theta, but we've already figured that out up there. Times the thickness of the cylinder, and we figured that out ahead of time. And this is for each value of I. Then we say the cumulative volume is the volume we've added up so far, because we're going to go through this loop again and again, plus this delta value, delta V, which I just calculated in the line up here. And then if I want to figure out the associated volume of everything up to that value of H, I add in the volume of the cylinder, which is this pi r squared times H. And I also add in the volume of the half sphere. So for every value of H, working my way up from 0 to capital H, I have the volume which would be included by the sum of these things. And if I want to know the total volume for capital H, I look at the last value, and here's another cute MATLAB command which says takes the last value of a vector. So back over here, if I go x sub END, it will tell me the last value of x, which was 8. So if I go v tot sub end, it tells me the last one from this whole calculation. Now, in this particular case, where I picked capital R equals 1, capital H equals 1, the last value should come out to be 4/3 pi r cubed, which should just be 4/3 pi. So let's just take the volume I get, divide by 4/3 pi, subtract 1, and that gives the fractional error. And then let's look at what we get. So I'm going to run this program, and I get that the volume of a whole sphere of radius 1 is 4.1887. I compare that to the actual volume, and I get this error of 10 to the minus 5. Yes?
In the for loop, why are you starting at 2?
I started 2 because I have to add up the cumulative ones from before, and I had to have this I minus 1 command. And I minus 1 has to be something which was there before.
What does delta R mean?
This here, that's supposed to mean delta little r,
Okay.
and that's the thickness of the of that cylindrical shell. And we calculated it up here as equal to delta theta times sine of theta. Yes?
What is the zeros command do?
The zeros command, I'll just show it to you over here. If I go x, I'll just use x again, is equal to zeros 3. This tells you something about the way MATLAB thinks. It fills in a 3 by 3 matrix. MATLAB just loves matrices. So I didn't want a whole matrix full of zeros. I just wanted a vector full. And so that's why I put x was equal to zeros, and I put 3 comma 1, which means make a column vector of zeros. And I could have, if I wanted, put x is equal to zeros 1 comma 3, and that would fill it in as a row vector. And okay, so I just filled that in so that to make MATLAB not have to be so busy worrying about things. Okay, well, what else can I do here? First of all, more MATLAB syntax. In terms of getting the output, I put DISP, and then I put something in quotes, and that means and then the output I got from that was the volume is, and then it gave the answer to the command. Now that doesn't look so nice. It looks nicer to write something like this. The error is, and have a number all just written out like that. So what I do, if I want it to look nice like that, is I want to display, and it can only display arrays. In this case, it's a character array. So I take a character array, which is made up of one character array and a second character array. And the second character array is the number I'm interested in. But the number I'm interested in is a number, not a character array. So I have to turn that number into a character array. And there's a command that does that in MATLAB, which is num to str, which means take a number and turn it into a string of characters. And then I get this nice output. So now I'll do it again, and I'll get this nice, What did I do wrong? Num to string v tot sub end square. It says undefined function or variable volume.
Oh, you deleted with volume equals, so when it says error equals volume.
Aha.
Yeah.
So I wanted volume equals, very good, thanks. Volume equals that thing. And now I run this again, and I get this tidy looking output. The volume is this. It would be nice to put a little more space in there, so I can put a space in there. I can put a full colon there. I can make a capital T here to make it look even nicer. And And I can put a capital T over here to make this look nicer. Now I'll run it again, function F5, and I get this nice output. The volume is this, and the error is this. Now, that's what happened when I divided this into 101 cylinders. If I put more and more cylinders, which are smaller and smaller, the error, which comes from that little triangle piece, gets smaller and smaller. So instead of putting 101 here, I put 1,001 cylinders and add these up. I get an error now of 10 to the minus 7. So I took 10 times as many cylinders, and the error between what I calculated and the mathematically right answer went down by a factor of 100. And if I increase this by another factor of 10 and run this again, it goes down by another factor of 100. So what we say is this converges quadratically. The error goes down as the square of the step size. I do 10 times as much calculation, and I get 100 times less error. And that has to do with the nature of how those little triangles at the top of the cylinders get smaller and smaller. Now that I've got this output, remember I've accumulated here in this for loop, I accumulated the volume working my way up to all these different values of h. So here in this calculation I said capital H equal to 1, but I collected a vector for all the partial values working up to that, which means I can now make a plot, and the plot I can make is a plot. Just skip this command here about vmilk for a second. The plot I can make is a plot of I'll just make that go away too, is a plot of h versus v total. So I run this again. I don't have to because I've been running the same thing again and again. And now I have a plot here which shows, depending on what capital H is, what's the volume of ball in the oil. So for example, when capital H is 0, the x-axis here corresponds to capital H equal to 0. I've got a volume of a little over 2. And remember, the total volume of the sphere was a little over 4. That's the half. Half the volume is in the oil if capital H is 0. That's the right answer, right? Now, if I increase H more and more of the ball is in the oil. By the time capital H is 1, all of the ball is in the oil, and that's what this little more than 4 is. That's 4/3 pi. That's the says the whole thing is in oil. Now what I want to find out is when is 2/3 of the ball in oil. So what I can do is I can say, let's look at what the volume of stuff in the oil is, as V oil. The volume in oil is supposed to be 2/3 the volume of a sphere. That's 2/3 times pi r cubed. And then I multiply by 1s because I want to make a graph of this. And now in my plot I also put H and I also put V oil. And now I make the plot again. And I get this straight line across. So I'm supposed to figure out what is H so that the volume associated with it, that's the y-axis, what's the value of H so that I get that the volume is equal to 2/3 the volume of the sphere. So what I'm looking for in the end is this crossing point. How do I figure out what that crossing point is? Well, I just draw this finer and finer and look closer and closer and find that crossing point. That's the Macgyver approach. So I've used nothing that you didn't know in high school to do this.
Except MATLAB.
Except for MATLAB. But there's nothing about MATLAB here that you couldn't have learned just as quickly in high school. Okay, so we have 5 minutes left, and I would like your goal here, like in every class, is to be able to reproduce this yourself afterwards without looking anything up. So the question is, what is it about this that you found vague, unclear, confusing that would make it so you couldn't do this yourself? Yes?
I was actually just going to ask if you could put this on maybe Blackboard or something so we could reference it.
I can, and I will.
Okay.
But will be, if I give you a homework problem that involves doing something like this, it will be all too tempting for you to take this code and just try to modify it a little bit and to get the answers that you want. So the learning experience, I am giving you an opportunity to skip the learning experience. So I will do it because you asked me to, and I want to be a nice guy, but I'm actually hurting you by doing it. I know this is the same thing teachers always say, but it's true. It's your goal in this class is not to get through the homework. Your goal is to try to figure it out. And I'm here to explain it right now, and you've got 3 minutes to try to understand it right now, on top of that posting, which I will do. Yes?
I didn't understand the vector part.
Can you pass in your homework, please? You didn't understand which part? What do you mean the vector part?
V total and all, like, what have you done, like, in the for loop basically, and before that, like.
Okay, so what I've done here is I've tried to describe 100 cylinders all at one time. After I've got these 100 cylinders, I can describe the volume of all these 100 cylinders. And that's this thing called delta V, which I could have actually calculated outside this for all 100 cylinders. I want to add up those delta V's to figure out the total volume of that weird shape. Rather than just add it all the way up to capital H, I do partial sums. So I keep track of the addition as I go along. So I got the first cylinder, then I've got the first plus the second, then I've got the first plus the second plus the third, the first plus the second plus the third plus the fourth, and that's what all of these V sub i's are. That means for every value of H, between 0 and the big value of H, I've got the number I want. So now I can look at all the little values of H, little h in between, and I can calculate the volume in the oil by adding up the partial sum associated with that, plus the cylinder associated with that little h, plus the half sphere.
But like in this one, like Vi equal to Vi minus 1, if you start from 1, if you start I from 1 and if you remove minus 1, won't it will still be the same thing?
It will come out very close, because always with these things, we're always, if you forget the first one or the last one, that just introduces a little error. But it will come out slightly different. If I put here an I, and I put here a 1, it will come out very close. But my error all of a sudden becomes it's small, but not as small as I'd like. Okay, because I'm missing something at the end. I forget, I have an extra one or not an extra one or something like that. And another question. Okay, yes?
Can you go over how you drew the green horizontal line again, just like
the way, so I have this green horizontal line I wanted, which is just a line across. And the way I did it is I said, well, I've got 101 values of H. And for each of those, I just want one value, which is the height. So there are all different ways of plotting it. But one way of doing it is I say, let's just pick 101 values of the number 1. And I'll multiply each of those by the number I'm trying to get. And this gives 101 numbers, so I can just plot straight across. Okay, just a quick show of hands. How many people think if I gave you 2 hours on your own that you could do this? Raise your hand. Okay, put your hand down. How many think you could almost do it? You've just about got it? And how many think you'd just be totally lost? Some of you. Okay, so now there's a correlation between who said they totally lost and where you sit, so we can fix that problem. You guys come sit in the front in the rest of the classes.